No, this is Physics 2, Lab 5, by Quentin Lumsden, me. So the purpose of this lab was simply to observe Faraday's law. Through that, I created a computational model and compared to the results of the lab. Essentially, the procedure here was we dropped a strong magnet through a copper tube, and then measured the time it took for the magnet to fall through the tube. So the overall results of the experiment, we resulted in an experimental time of 13.2 seconds, and when we then simulated the same thing, um, we got two different computational values estimates. The first one was with um, a dipole moment value, a mu value of 1.8855 amperes per meter squared, and this gave us a time of 35.148 seconds for the magnet to fall through the tube. And the second value we computed was then an attempt to match the experimental time, and this resulted in a mu value of 1.154. Um, Again, the first value was the same as our experimental value we found in lab 4, and the second value was essentially found through a process of trial and error until it matched with the experimental time. So a few fundamental concepts to remember here are Newton's second law, simply F equals ma. Newton's third law, that each force has an opposing force in the inverse direction and of equal magnitude. Biot-Savart's law when it comes to calculating magnetic field. Also, Lenz's law is very important to remember, with Faraday's law being tied into that, and as well as Ohm's law. So as we look at the simulation, why can't we use a ferrous tube like steel, for example? So this is simply because the magnet will be attracted to the walls of the pipe. This would then call that Lenz's law. This would then mean that Lenz's law would not be the only thing causing the essential breaking of the magnet. Um, there would be other forces at play aside just from the magnetic field and gravity, because you'd have the actual attraction to the wall itself, so you'd have more forces going on there. And then what would happen to the magnet? What happens to the magnet? How does it compare to the magnet falling without the tube? So, induced fields inside the copper tube create a field which acts as a brake, slowing the fall compared to without the tube. So, essentially, Lenz's law states it will be a field in the opposite direction. The induced current will produce a field in the opposite direction of the magnet falling, and then that then acts as a brake. So here's the code, and here you can see the initial values, and the geometry of the tube as we set it up. And for the experiment, for the computational model, we set we made the tube 4 times shorter than it was for the actual experiment, and this was done for the sake of time and to make results more accurate. Over here, you can just simply see that again we're kind of more initializing the magnet itself, and establishing the dipole, and the mu values. Then finally calculating flux. And then here you can see we're then now actually simulating it falling through the tube. And then on the second thing, you can see we then go to calculate the net force and the velocities of the magnet, and then finally we calculate the total time it took to fall through, and we times that by 4 for a comparison to the experimental value. So here are the two graphs. On the left, you can see that is with a mu value of 1.152, I believe, or 8, or 3. So it's around that range. So the value, which we then got a time of 313.2, and the other one is the 1.8855. Which gave us a time and tube of 35.148. And interesting enough, you can see that both of the graphs are very similarly shaped. However, one is spread out over a longer distance, at least the center of it is. So a few assumptions we made within this lab is that gravity and magnetic field were the only things exerting a force on the magnet, and that the axis of the tube was aligned with the dipole moment of the magnet. A few possible errors. We could have inaccurately calculated the dipole moment. This seems to be evident based off our data from the last lab and from how the very large difference versus the experimental value. Also, errors when timing could have resulted, and also just general errors in coding and calculation. So, a few continued discussion questions. So, what would happen to the system as a whole if we flip the magnet around? Well, you might think, oh, it would fall faster, but no, it will reverse the direction of current, but the tube and the tube of the motion remain unchanged. So, the um, the flux will it will reverse the direction of current, but the magnetic force will still act in the opposite direction of the magnetic force produced by the magnet, still acting as a brake. So the motion will remain unchanged. And how does the tube in the real world system compare to the computational system? The computational time was significantly faster, likely because it did not include air resistance or possible friction from the tube. So the values really didn't line up. The values really didn't line up. And also mu values were likely wrong. Um, and also, what does the velocity versus time graph tell you about the forces acting on the magnet? This says that the net force is zero throughout the tube, as the velocity is constant, aside from the beginning and the end. So the velocity is constant. That means that the force of gravity is always equaled out by the magnetic force induced by the tube, and that gives us our constant line. So a few last what ifs. What if the resistivity of the conductor were reduced as close as possible to zero? How would this change the falling magnet? The magnet would fall slower because the induced current would be higher. Um, this then results in a stronger magnetic field, which again is why we have the magnet falling slower. So what if we cut holes or slots into the tube? How would this affect our model? So the holes in the slot would disrupt the magnetic field, causing the magnet to end up actually falling faster. That's it, and thank you.